everyone. It's my pleasure to introduce to you Nayara Pinto. Dr. Nayara Pinto is an ecologist with NASA Jet Propulsion Laboratory in Pasadena, where she works on applications of synthetic aperture radar observations. She is the science coordinator for UAV SAR, a NASA facility instrument, and a testbed for spaceborne SAR sensors. Nayara's research focuses on development and testing of algorithms that to map vegetation biophysical parameters that can be integrated in ecological and business models. These include canopy height, or over, and distribution of perennial crops. She's funded by NASA's Applied Science Program to help advance open science and train a new generation of end users to take advantage of the golden age of SAR. Nayara, thank you very much for coming. The floor is yours. So yeah, thank you very much for coming. It's a pleasure to have you here. And the floor is yours. Thank you.
Thank you. Let me see if I can start my video. Give me 1 second. Okay. So thank you everyone for coming to my talk. I am an ecologist working with remote sensing. So the nature of what I do is very interdisciplinary. I try to make this talk as high level as possible. And if you have any specific questions, feel free to interrupt me. I take that there can be that there is a moderator there. Perhaps you, Casey, if you want me to stop, let me know. The title of my talk is Unlocking the Power of Radar for Mapping the Amazon Forest Agriculture Interface. Oh, I'm having trouble with my own computer with the. Let's see. Okay. I hope you can still see my screen. If not, let me know. I have several co-investigators on this project: Savannah Cooley, Lyndon Estes, Andrew Fricker, Jonathan Ventura.
Sorry to interrupt you. I guess we lost our presentation now. So can you try to share it again?
Yes. Yes, of course, we'll do. Let's see if I can share it again. When I was sharing, I couldn't change the slides. So let's see. Now, can you see it?
Yes, we are seeing it.
So now let's see if I can put it in presentation mode. Okay, can you still see it? Yes. Okay, cool.
Thank you.
So this is our list of co-authors. We have a very nice group of people who have expertise in land cover mapping, GIS, remote sensing, and statistics. And the main motivation, the context for this study is to understand the drivers of deforestation, not to map deforestation itself, but understand what's replacing the areas that get cut down. This is some statistics from national monitoring systems in Peru on the left and Brazil on the right. And it shows some varying trends on deforestation. These are national trends, and they're mainly driven by the expansion of the road network, commodity markets, and human migration. And I'm really interested in the forest agriculture interface. I think this, as an ecologist, this is where a lot of action happens. You have a lot of simplification of the native ecosystems, and you also get to understand how diversity gradients, the human-induced diversity gradients are happening. My focus here is understanding the expansion of perennial crops, especially oil palm, cacao, and citrus, so tree crops in general. The main knowledge gap here is deforestation attribution. So what I'm showing here is some deforestation maps from national platforms if you look at the Brazilian platform on the right, it's called PRODES. It's an excellent system. And what you see in yellow here is areas that have been deforested. And after they have been deforested, they can go back to forests, they can turn into secondary forests, they can be converted into pasture or villages, anything. So the challenge here is to understand what happens in these yellow areas. And again, the focus for my work is in perennial crops. And the reason why is because I work with radar, and radar has some presents some unique opportunities to tease out perennial crops from the surrounding forest. And as you can see here, the color and the texture of the forest is very similar to the perennial crops. If we were working with other crops such as soil, or if we were working with pasture, it will be much easier to differentiate from the forest. So we're trying to infuse some remote sensing technology into this question. When it comes to ecosystem services, the impacts of the expansion of perennial crops is not well understood because there's a lot of variability in the management in the different countries. So I'm just putting some examples here. This Nature paper was published just recently. And another paper with the exact opposite argument for Brazil was published last year. That those two are for cacao expansion. When it comes to oil palm, we know that oil palm is not native to South America. It's not native to the Amazon. So the opportunities for conserving biodiversity can be low. But the main question here is whether oil palm is expanding over primary forests or degraded areas. Ideally, it would expand over degraded areas. It wouldn't take high carbon, high biodiversity forests, but sometimes, as you can see in this study here, that's what's going on. So the way to understand this, you have to have the two pieces of the puzzle. You need to understand where deforestation is occurring, and you need to understand where the perennial crops are moving. And within each one of those crops, you also have significant variation in the management system. So one of the things that I learned in my field trips as part of this project is that not all cacao is the same. And I don't know if you ever stop to think about this, where my chocolate comes from. First of all, it's not Switzerland. The seeds are coming from a tropical country, and they're mainly grown in smallholder farms, small areas, and there's a lot of variability in management systems. You have this case here where you only have cacao, so it's a monocrop, and you have systems where it's associated with other economically interesting species. And you also, such as in this case here, you have acai, and you have agroforestry systems where you have a few native trees shading the cacao trees. So as you can imagine, these have very different outcomes in terms of carbon dynamics and biodiversity, potential for conserving biodiversity, hydrological patterns, and evapotranspiration. So if we want to tip the balance away from deforestation and towards sustainable systems, we have to think about how sustainable food chains can be implemented. So again, this is the motivation for a robust monitoring system. And the gap that we're trying to fill here could potentially support efforts for crop traceability, where people understand where their seeds are coming from that were used to make their candy bar, for example. And then also provide investments for sustainable practices, because doing something in a sustainable way does require money, not just goodwill. So you need to invest in order to get those sustainable systems. The project that I work for is a part of a NASA Applied Sciences, and it's a program called Servir. And their main motivation is to bring space to village. So bring tools and services to end users at the countries where there is most need for data. So I've been working a lot with this group. And my small contribution to this effort, to this larger effort, is to bring in some expertise in radar remote sensing. We have a lot of new opportunities this decade because we always knew that radar was good for mapping vegetation, but we lacked consistent global data sets. They were also free. And now suddenly we have a wealth of data. And next year, we expect that NISAR will launch, providing public data sets for L-band. So even if you're not familiar with radar, I think what's important to know is that different sensors are sensitive to different aspects of the vegetation. So by combining them, you get a much better picture of the land cover patterns. So in this case, starting next year, we expect to have 3 wavelengths. So you get some sensitivity to short and tall vegetation. And the data sets are also free, which means that we can ensure reproducibility by our end users in principle, if they have the processing power. And that's something that I'd like to talk about in the end. And we also have more regular temporal sampling, which is something that we didn't have before. We had, for other sensors, we had the opportunity to get some radar data, but in this case, we know that we're going to get data roughly every 2 weeks. And these data sets are cloud-free. The goal here that we have is not to develop brand new algorithms, but to operationalize what already exists. Just choose between a couple of different classification models and help implement them in local monitoring systems. In Peru, the monitoring system is called Rio Bosques, and in Brazil, it's called Terra Class. So they're both concerned with deforestation attribution, and they usually have a layer that includes all of agriculture, but so far there is not a good operational way to make a distinction between perennial crops and annual crops. These are the 2 study areas that we are working on. One is the Department of Ucayali in Peru, and the other one is State of Pará in Brazil. And in both of them, you can see a lot of expansion of agriculture. In Ucayali in particular, there is a plan for expanding oil palm. And in Brazil, there is an expansion away from the roads in the Trans-Amazon area. And right now, this is the main cacao producer in the country. So the advantage of radar is being able to complement what we can see with optical systems. And optical systems are closer to what we can see with our eyes. They're very sensitive to color and chemistry. So in this case here, a lot of these vegetation types look similar because there is a high level of greenness. But if you bring in a radar, and this is a false color composite, you can see a lot more variation. And you can also see areas that are inundated versus areas that are dry forest. What you see in purple here and pink is inundated forest, and the areas that are mostly green are likely to be dry forest. So the fact that the signal can penetrate through the canopies is really useful to us, especially in the Amazon, where you usually want to make a distinction between inundated areas and dry areas. So this is an overview of my model. We are combining everything that we can, not just radar. We are using some NDVI, which is an index of greenness that can be obtained from a satellite that is operational right now. We obtain training points and get the signatures. From the signatures, you develop a simple statistical model. This is a Bayesian model that will output a probability map. So for each pixel at 30-meter resolution, we have the probability that the pixel will be oil palm, for example. This was our first round, was with oil palm. And at the end, you develop some sampling strategy for conducting field validation, which can provide more training points to continue this until you have an acceptable confidence level. And again, the reason for using multiple wavelengths is because they have different degree of penetration in the canopy and interaction with the vegetation elements. So they provide different information that's complementary. The first step that we developed with our local experts in South America was the development of a land cover key. And it's really important to emphasize that the difference between land cover and land use, because you might have the same crop in very different stages, and that's going to give you very different remote sensing signatures. So we really had to keep repeating this. And so we could have training data that could better be reconciled with the remote sensing observations that we had. And this is one example here where you have a young plantation, which has a lot more ground exposure, and a mature plantation that's more closed. And even though it's the same crop, I would deal with them as different models and different classes. Because the radar is sensitive to the ground exposure, I expect to see something completely different in those two cases. Our next step was to develop a land cover database. So based on some points that we obtained from local experts, so farmers, farming cooperatives, we used high resolution optical data from the Maxar sensor to just manually delineate polygons. These polygons have been published for reproducibility, so we want people to know exactly where our inputs are coming from. So far, the polygons are published in a Dataverse. And we have an ArcGIS online page that's shown here that you can go and explore the data sets. And we keep improving on this. We are finished with the oil palm component and currently working with the cacao component together with some cooperatives in Brazil and in Peru. Then after you have a map that has a stratification of likely oil palm and likely not oil palm, for example, what we do is we develop a random sample using the collector's platform. And this is a way for getting points not only inside the polygons, but also outside, right? We need areas that are likely not belonging to our crop class to develop a statistical model. And we want the sampling to be random. And so we came up with a number of random points, and each point is interpreted by 3 people because we also notice some variability in terms of interpreter confidence. So our technical approach so far is to use Sentinel-1 and ALOS Pulsar, We expect to get NISAR data, which is the NASA satellite, starting next year. That's going to be a game changer because the temporal sampling for ALOS pulsar is not the same. We roughly get the data once a year. We're using Amazon Web Services for now. We're working on the Oregon data lake, and the reason why is because this is where the NASA repository is. So we're trying to do our analysis in the same locations where the data is located. Again, we have a calibration validation strategy that where each point is labeled by more than one interpreter, because we know that there is some variability there. And we provide a 30-meter resolution probability map at the end. So these are some results that we recently got with the oil palm. So what you can see here is a false color composite of 3 bands. In red, you see a radar volume index from C band. In green is a radar volume index from L band. And in blue is NDVI, which is a greenness from optical sensors. So essentially what you see there that's green is forest. And whatever is red is bare ground or short vegetation. So the other areas that are in blue and purple are areas that have very low volume. So they don't have a lot of green. Okay, so very low canopy volume, but they're also very green. So these are areas of palm canopies, right? The palm canopy is much thinner than a forest canopy, thus you have less volume, which is what the green band here is capturing. But you're still doing photosynthesis, the leaves are very green. And so that's why NDVI is high. This is one example of a very large industrial plantation that I usually use as my benchmark for the classification algorithm. So you have these really large ones, and you have these along the road. As we mentioned before, a lot of the expansion happens along roads. And we have areas that have similar signatures, and these are native palm trees. They're called aguajales. So quantitatively, we were able to tease out these aguajales from the plantations, because the plantations are more regularly spaced, whereas here in the natural palms, you see a lot more variability in the canopy. So our goal is to have a cloud neutral process. We're not there yet, but this is the dream. And at the end of the assembling all the data layers in AWS, being able to push them to Google Earth Engine for those who prefer to use Google Earth Engine, and also send it to the server at the end user location. So if they want to do any work on premise, they can. But so far, we are working on AWS and have some more limited presence in Google Earth Engine. Some of the results we see is that we're getting a much better interpreter agreement for mature oil palm compared to young oil palm, which is expected because young oil palm is just messier class. We keep insisting on this because young oil palm is, of course, what replaces deforestation, right? If you want to see what happens right after, you need to have a good handle on that class. And this map here, the orange is a data set that was produced in 2015 in Peru. So we're seeing, and whatever you see in pink is our model. So you can see here some overestimation, an area that was just some other type of forest that was classified as oil palm. And we were able to see the edge here So we observed some of this in Peru. We're getting very good agreement in general. So what I expect to see is just some small changes in area, but more than anything, being able to automate the process and also to include local experts in all aspects of the classification. Again, this is a comparison of our data set in pink with the 2015 map. And we can see here there is some underestimation in some areas, and this is because this model is for mature palm. So we expect that if we run a model for more open young palm, we can get more polygons in these areas. Some of these areas might also be areas of mortality, and the areas where you have houses, which sometimes, because this was done manually, sometimes interpreters will include everything. It's very hard to just digitize the plants and remove everything else. So far we're getting good classification accuracy for oil palm. Our goal is to move on to cacao after this is wrapped up. And cacao is a much more heterogeneous case because well, the oil palm obviously is a palm and it's introduced from Africa. Cacao is an Amazonian crop. So we expect to see a lot more confusion. The other thing with cacao is that we don't have those really large industrial plantations. I think that's the case in Africa, but not in South America. Most of the crops are grown in small holder farms, and the area is usually less than 5 hectares each. So with that, you get a lot more noise in the radar estimates, and we expect this is going to be addressed by NISAR, but we have to try it next year and see for sure. So far, it looks like we have good separability between tree crops and palm crops. So what you see on this table here, on the right here is tree crops, and on the left are the 3 palm crops. And the RVI is L-band radar volume index, which is an index that's used to just look at the proportional contribution of the canopy versus ground. So it might be that at the end we will have to join some of the tree crops and do some better assessment to differentiate it from the forest, and also join all the palm crops to be their own class. In other words, we might have structural classes, and we might not be able to, we have to see if we're able to differentiate those 3 classes in a robust way without too much overfitting with our classification model. The next steps that we want to work on is to improve our reference data. We're hoping to use some LiDAR data, which gives us some information about the vertical structure of the canopy. The challenge with the LiDAR data is that it's sparse. We don't get the wall-to-wall coverage. But it does provide some really good training data to allow you, for example, to ask what the differences are between a cacao monocrop and a cacao agroforestry. So with enough samples, we expect to be able to answer that question. And it's one of the things that might allow us to better understand the ecosystem services that these agroforestry systems are providing, and perhaps support a system of payments to farmers, which doesn't exist yet because the connection between carbon payment systems and food supply chain is still a bit weak. Some of the challenges that we have here is to implement a reproducible model that's reproducible for us, but also for end users who don't have the same cloud resources that we do. So just one of the things that I learned is that just knowing that the imagery is free is not sufficient to make the process reproducible, because there's many other components to reproducibility. People need to be able to pay for storage, for example. They need to have the same environment as we do in order to run the algorithms. And they need to have access to processing GPUs. So we're looking at the trade-offs between these different systems. For example, Google Earth Engine and AWS. Keeping in mind that NASA is putting their assets at Alaska Satellite Facility, their SAR assets, which means if we want to work close to the data, we need to work in AWS. However, many of our users are very comfortable with Google Earth Engine. So essentially the challenges that we have are to define the right architecture for different users and remain flexible. So for example, I can develop a classification that works on my computer, but then implement it in Google Collaboratory. And just try to steer away from monolith solutions, which means I might need to use different tools. I might need to be cloud neutral. You might need, for example, to build a Docker image to run things in different servers. And you won't necessarily be able to port everything to Google Earth Engine. So just make a solution that is more modular, I would say. And then also work with the end user in terms of finding a cost model. So what's something that's not clear to me, especially working in a context of governments that are changing, is how much people are willing and able to pay for cloud services, right? If we move away from Google Earth Engine, how are they going to pay for storage? And will Google Earth Engine remain free? That's the other question. So those are all architectural questions that we need to think about if we want to implement open science. So the main lesson that I learned here is that just having the free satellite data was not sufficient to ensure reproducibility and scalability. And finally, I just wanted to wrap up with what we think is our theory of change. We're hoping that by having a robust monitoring system, this is going to open the possibility for more traceability and perhaps better payments for sustainable systems. And these are some examples here. It's not the full list. So one example is to provide payments for or incentives for expanding over areas that are already cleared. These areas that you need money to be able to use them, to go into an area that has been degraded. That takes money. You could also pay more for pods that are coming from agroforestry zones. And we already saw this implemented in some places. The seeds, the products that are produced in agroforestry areas, they are usually going to international markets, and they might get a better price. And the third option is to make the production more intense, so you have more production per unit area. So discouraging or minimizing expansion again. So this is what I wanted to present. It's a very high level view because I am not sure what your background is, and I'm open to answer any questions that you might have, and I'm really happy to be part of Earth Labs. So if you have any ideas for potential collaborations, or if you're interested in remote sensing at all, if you're interested in an internship, let us know. Thank you.
We had some applause here.
Thank you.
Thank you very much, Nayara. I really appreciated your presentation. It was great. So any questions from you? Yeah, go ahead.
Yeah, should I come up, Nayara? Can you hear me?
I can hear you. Yeah, this
Okay.
is perfect.
Yeah, so I'm interested because and this is, you know, probably my bias growing up in a very temperate zone, but the first time that I went to a tropical area was in Ghana, and I was just really surprised because you see all these, like, when people talk about deforestation, like the images that they put up are like, you know, logging operations where there's a huge amount of erosion and stuff, and like it took me a while to adjust to like seeing these, yeah, like cocoa plantations and stuff that were also deforested, and like recognize that as deforestation. And so I'm just curious if you guys think about ways to use your models and data to communicate that to people who aren't familiar with what deforestation looks like in tropical areas.
I never thought about this. So how do you think we should, what would be the best way to show this? Maybe to show the entire sequence of clearing and then regrowth?
Yeah, I think maybe just food for thought out there, but yeah, that sounds like it would be great. And then some of your kind of false color images too, of like showing where places are, maybe that could be really interesting. Thanks for the talk.
Thank you. Yeah, that's a very good suggestion. We need to not just show that huge wall of green, but rather represent better the mosaic.
I have a question. That I'd like to understand better how is the process of citizen engagement that you have within Server, like since like the beginning, getting information from them to do all this process, and then the transference. You talked about a little bit of the transference, but I mean, in the very beginning, how is this engagement? What do you learn from that process? Can you tell a little bit about it?
Yeah, so Servier has a series of hubs, and the Servier Amazon is the youngest hub. I think they were established 4 or 5 years ago, and they are excellent. They have centers in Colombia, Brazil, and Peru. It's a consortium that includes local institutions in those countries. And one of the first steps that they do is to build a stakeholder map to understand who the players are and what their needs are for technology. There is some data scarcity, but at the same time, there is a lot of knowledge. So you really need to work with them to understand exactly what the technical gaps are. For example, if I just showed up with a general land cover map, nobody would be interested in that because they already know how to do it. People understand optical sensors, right? But it's just might need more help to start to adopt radar. Radar can have some counterintuitive aspects to it. So where can you work to lower that barrier? This is where we try to think about as we talk with the stakeholders that Servier identifies for us. And with all of that, things can be very fluid because governments change. So the other approach is to just spread your bets as much as possible and find people at the federal and local level, and government as well as academia. That was the other thing. So one of the programs we worked with was, finished, and governments changed because of election, and some of the people that we were a point of contact are not part of government anymore. So we have to just remain flexible. That was the strategy for engagement so far.
Thank you.
I have a quick question. Can you hear me?
Yeah.
Cool. That's really interesting talk. One thing I noticed in the false color imagery was a lot of salt and pepper effect of the, especially the not deforested area. The natural areas seem to have a lot of differing, and very like heterogeneous structure. And another thing I noticed was you mentioning trying to get rid of small single pixel classifications that were not in a bigger cluster. I'm wondering how you're planning to approach tackling that issue, and if those are kind of like related issues in your head.
Yeah, totally. There's two parts to it. One is to remove speckle, which is part of radar. It's just the nature of radar. And what I plan to do is to do some temporal averaging, and that's going to be easier with NISAR, because with ALUS, I only had one image per year. So that makes it very noisy. And by averaging, there are papers that show exactly the statistics and how many images you need to average in order to get what they call equivalent number of looks to be able to have a sharper image. And the other thing is to work with segments and not pixels. And that's one of the things that I'm working with JPL, the data science group here. We're looking into a segmentation approach, especially knowing that some of the oil palm, at least, they have very regular shapes, which are very different from natural features. So if you exploit that, you get rid of a lot of spurious classification. There's also more traditional methods like image morphology, where you can clean up your image in the end. And I think that's going to be unavoidable. At the end, there's going to be some isolated pixels that are removed this way. We just set a threshold, and they are deleted from the classification during post-processing.
Thank you.
Thank you.
No, what, I have one more. Go ahead.
Thank you so much for your talk. This is Jennifer. My question is related to SPG on the horizon. Do you think the models would get better with SPG, or do you think they're going to be good enough? SR, we can call the work done.
I think they will get better. If anything, the confidence will be higher, even if you can get something with a radar. My main concern is having overfit, having a model that works really well locally, but it's not going to be applicable globally. And as we infuse the hyperspectral into the classification, I expect to see more robust models, especially because, Cacao even the cacao that we grow in Africa, it's originally from South America. So I expect to see some similarities there. I might be wrong. It might be that during the, the breeding and selection that they have very different signatures. But in any case, the distinction from the surrounding forest, especially if it's degraded forest as well, could benefit from hyperspectral. And also understanding the different management practices could also benefit. So we're not married to any particular sensor. We want to use everything that's available. The focus on SAR here is because that's what's available now, and this is what I know. And we noticed that there is some barriers to adopting radar by the end users in environmental sciences in general, and in South America in particular. So if you want to work with radar and SPG, let me know. Send me an email. That would be, the dream, I hope before I retire, I can do that. Get that to work.
So yeah, so my last question is I would like to understand to hear from you how excited you are for the NISAR and biomass, and how like the synergies between both of them, how they can improve your maps, and in general, like for earth science, environment science in general, what we are expecting from them.
I'm very excited because when you work on a mosaic, like the places where I work, it can be surprisingly hard to find what they call high conservation value forests, which are forests that have high biomass. Every now and then you see a patch of forest that's very tall and looks like it's a high conservation value. And it's just very hard to map them operationally. And they're incredibly important because they're islands in a very disturbed system, and they become stepping stones between conservation units. So I'm hoping that with the P-band, we're going to be able to do this. To some extent, you can do that already with JEDI. The challenge with JEDI is, again, that you don't have wall-to-wall coverage, right? You have excellent calibration and validation points, but you still need something to extrapolate beyond the footprints. And that's where all the error is, or most of the error is this extrapolation step.
Thank you.
Thank you. Yeah, let me share my screen again so you can see my email. And if you guys have any additional questions, or if you're interested in collaborating or interested in an internship, let me know, or send me your students if you're too senior to be an intern. If you're past that stage. Some of us are.
Thank you.
Thank you.
Thank you.